There she is, our beautiful sun. Have you ever wondered how it radiates so much energy? I think we all are familiar with two words, right? Nuclear fusion. Fusion occurs at the core of the sun where the temperature is about 15 million degrees Celsius and the pressure is immense due to the inward gravity. All the atoms are in a state of plasma. What actually happens is 4 protons come together to give a helium atom, 2 neutrinos, 2 positrons, and energy. No, you're wrong. What actually happens is, the sun actually requires 6 times more temperature for fusion to occur. Hence, it uses the beautiful phenomenon of quantum tunneling. Let's say I entrap my brother within this suitcase, but for our purposes we'll interpret this as a potential barrier, as in he will require a high amount of energy to get out. As you can see, even though he's trying so hard, he can't get out, unless an external agent provides him with an opening to escape the barrier, like I am doing right now. But if we consider him as a subatomic particle, there is a 1 by 10 to the power 28 of probability that he'll find his way out. However, for the remaining probability, the particle would exist in a quantum superposition of states where its position and velocity would vary at every instant unless we measure it. It won't be 100% precise like this picture though. This is given by Heisenberg's uncertainty principle. We need to understand a few things beforehand. In 1924, de Broglie proposed that all matter exhibit both properties of waves and particles. That was shocking. Even he couldn't interpret the physicality of the wave. As Schrödinger came in, he devised his famous wave equation whose solution was the wave function. The wave function could be simply interpreted as the mathematical representation of the wave. He thought that the charge of the subatomic particle was dissipated throughout the wave, but that was not the case. That's when Max Born came to the rescue with his Born rule, stating that the modulus of the wave function square would be the probability of finding the subatomic particle at the particular position. Later, quantum field theory was proposed, which assigned a field to every domain of particle, stating that the particles are oscillations of the field. Anyways, to explain tunneling, I'm gonna use a photon, as you guys are familiar with its field of oscillation, the electromagnetic field. The flow of photons is the oscillations of the electric and magnetic fields varying sinusoidally. Let's say we release a photon into this potential barrier. Since it has nowhere to go, it gets reflected. But then remember how light is an oscillating electric field? An electric field cannot be discontinuous at a boundary according to Maxwell's boundary conditions. Hence, at the boundary, the electric field starts to decay exponentially close to zero. The envelope of this decay is called the evanescent wave. As you can see, before the evanescent wave could decay to zero, it has seeped its way through the outside of the barrier. This is due to the narrowness of the potential barrier. This principle governs our beautiful phenomenon, quantum tunneling. Out of almost 10 to the power of 56 protons in the sun's core, about 10 to the power of 28 of them overcome the Coulombian repulsion to undergo tunneling and provide us with the energy we need to survive.